Okay, so I think welcome back. So before we resume, quick tip for the target or if else for in general. When you have, in C in particular, when you have the ability to not use curly brackets, the same with target. In OpenMP, you can write pragma OMP target, not put curly brackets, and just put a statement after that, and the following statement and just the following statement will be on the GPU, or the target. When you have this ability to not write the curly brackets, do not take it. I'm part of the very old school people who will tell you, always put your curly brackets. Why? Because you know what happens. Oh no, but I just have one statement. Yes, for now. In 5 minutes, you're going to think of something else. You're going to put a next statement, and you will never remember that this next statement is not in the if statement, or is not in your for loop, or is not on the GPU. So please save yourself hours of trouble and nerve crisis just by putting your curly brackets. So let's quickly correct the exercise, and then we dive into the crunchy stuff. So where we're up to here. Data mapping, yes. So what did you do in, that's next one. Fine. Oh, that's the mirror malloc. Okay. So here what we have is we have a function called mirror malloc. The idea is this function will allocate data both on the host and on the device, okay, without triggering data transfers automatically. Okay, that's the idea. So if we look at the code here, simple code, we just allocate a data both on the host and the device of a given size, okay, a kind of malloc on the GPU if you want. Then we're going to do some calculation on it and effectively delete it when we're done with it, okay? So you have two ways to do it. We start with the version A, that's the malloc. Okay, so version A, in the mirror malloc, what did you do here to allocate the data on the device? Did you find how to do this? Yes, go ahead. Yes, yes. Okay. I think I need to remove the comment at the start. Yeah. If I try to allocate P, did it work when you did this? Yes? No? Okay. I have conflicting answers. It worked for you? Okay, because I thought maybe we had to pass the actual range behind the scenes. Without passing the range, it worked? Okay, let's try without the range first. Okay, so now we have unlocked the data, so we need to free it. So how do we free the data? Yeah, P. How do we free the variable P? Yes. Pragma when P target exit data. Oh, I'm sorry. And what comes next? Okay. Sorry? In this case, there are no calibration. I was being careful. I said, when you have the ability not to use them, but in this case, there's no curly brackets to begin with. It's what's called a standalone directive. Do you remember a standalone directive yesterday? One that I said, you don't need curly brackets for CPUs. It was a synchronization construct. Exactly. barrier, you didn't have the code associated with it. So you didn't have curly brackets. It was just a standalone. It's the same thing here. Target enter data, target exit data, they are both standalone. Remember, actually that's exactly what we were looking for in the first place. Because we can use the data environment, target data, which has curly brackets, but you can use it only when you know exactly what's going to go in it. When you have the start somewhere and the end somewhere else, you no longer have this ability. So this is why you have two standalone directives to allow you to put them wherever you want. So that's why there's no more code associated with it. So no more curly brackets. But well spotted. At least I know that if I have one curly bracket missing somewhere, I'm definitely going to be caught on it. So that's good. It's what, sorry? Okay, we're going to see, I guess. So where we're up to here, we have the data on the GPU, then we have the target map. Okay. Let's see if it complains when I compile, before I move to the second version. Okay. I'm just going to copy the reservation. GPU 1. Remember to remove this little space here, so that it actually becomes a special command and not just a comment. And do the same thing as last time. While I keep watching, it doesn't move, and when I move on, it does it. Totally knew it. Totally knew it. Now it's not happy. Variable in data clause is partially present on the device because there's something missing here when we allocated it. It's when we allocated P, we didn't give any number of elements, so it thought that it was going to be just one, just a classic integer. And we say, no, it's going to be an array. Yes? Unless I'm doing something wrong here. Yes? Sorry, say that a bit louder, please. Oh, yeah, true. True is 2 is the value in main. You're absolutely right. It's length. Yes. Oh, is it length or len? Length. Okay, perfect. So I'm going to go in that memory location, and I'm going to start to allocate enough from the first element, and I will allocate that number of elements. Okay. So now on the GPU we have the full array, not just the first element. Yes. For the same reason that free doesn't. Because when you do malloc, you need to give the size. When you do free, you don't. Because somehow the operating system has that information stored somewhere. And when you want to free data, free a memory location, it goes right to that memory address and frees the corresponding block of data. So until you say at first how many bytes there are you want in that block, it doesn't know. As soon as it has allocated a block of 10 bytes, it knows that there are 10 bytes in it. So when you want to free, it knows it frees 10 bytes. Yes? Yes. I would think so, yeah. That would be surprising, but yes, I would think so. Oh, yes, typically, but if you want... There are always, I guess, some exotic scenarios where you would like to do something exotic. The non-exotic version is this. So that's the first one. Oh, I didn't... I fixed it now. Let's compile, let's submit. Yeah, I know. When I'm looking, you're not doing anything. Yeah, I know. And then, so the version A is the version a bit harder because you have these target enter data, exit data. So that was the version A. Okay, now that 448. It means we're missing something here. Aha, of course we're missing something here. So far what we have is, we have allocated data on the GPU, there's some calculation on the GPU, and we're deleting data on the GPU, okay? In other words, I never sent data to the GPU, and I never fetched data back from the GPU. So I just made something happen on the GPU, but basically I kind of didn't care because I was just printing my own value anyway. So we're missing two things here. How do we punctually send data to the GPU? There's a target we've seen. Yeah? I just had the last word, 2. Yeah, and what's before 2? Map. In this case, no, actually. What, sorry? Data map, not this one. That's the one. That's the one. So here, before I start to do A0, A1, I need to send the data to the GPU. And it's like, but we already have 2 from here, so it should be sent. No, because remember, every time, if you just have targets and targets, yeah, the map applies. As soon as you start to do data environments, whether with the curly brackets or with enter, exit data, the whole point of these is to prevent these automatic data transfers, okay? So they no longer happen automatically because you're making sure that actually they don't by doing these allocations yourself. So that's why you have instead this other way to send data to the GPU or fetch data back from the GPU at any point in time. So with the target, you are definitely on the right track. So what do I write here? Pragma, OMP target, update, okay, and then? Then to what, sorry, 2? After that? Okay. Up. So now I'm sending the data to the GPU. I allocated it, and I now send data to the GPU. The GPU is doing the increments. Okay, now I need to bring it back. How do I do that? Exactly. Okay, perfect. Normally, yeah, we have 2 GPU. Normally, we have 2 GPU nodes, 8 GPUs per node, so that's 16 GPUs. So we can have 16 jobs concurrently. So since we're 50 people, normally it shouldn't be a problem. Ah, now I have 125. So 123 plus 1 plus 1. Now we're good. Now the second version with B already gives the right answer. Why? Because it's on the CPU. Now we're going to move that to the GPU and try to see if we still have this answer at the end. So the other way to create a data environment is how? Okay, we ordered the GPU, but we have all these automatic data transfers. Okay. What's the other way to create a data environment? So we tried enter, exit, and there's another one. The one with the curly brackets. Target data, yeah. Remember the rule. Worst case scenario, you say something that's incorrect, nobody dies. It's the whole point of learning. OMP, target, and then data. What did you put then after the target data? Yes? That sounds good to me. Then we put a curly bracket here. I've not forgotten it. We move all that there. Okay. If we did everything right, it should be the same result. Yes? Hmm? Absolutely. First of all, I'm quickly going to print the output. Yep, same thing, so it's correct. Let's get back to the output. Yes? $87 and what after that, sorry? No, we do. We're going to have that data transfer as the two. We're going to put that data there. Yes. Yes, exactly. So now we've saved these two data transfers. Well, we saved one in total in this case. Okay, yes. Oh yes, before using the, yes. Because what we did here was, the first time, we were executing on the GPU, sending the data, bringing it back. Sending the data, bringing it back. So we had the right result, but we were sending the data twice. What we did here was to keep correctness while also saving the number of data transfers. So effectively, we've now optimized our program while preserving correctness. Make sense? Yes. Full scope, and then after that, the data, what, sorry? And data environment. Yeah, that's totally what you can do. Typically, what you want to have is as much code as possible in the data environment. Why? Because that's as many data transfers you're going to save and as much performance you're going to gain. So yes, typically you will have more than 2 targets, hopefully, or the data will be much bigger than 2 integers. Yes. Absolutely. So version A, I had to design the code so that the starting point and ending point of the data environments are in separate functions. So inside that function mir malloc, I cannot just use target data because here I would have like an opening curly bracket just before the return, but I cannot put the rest of the code because the rest of the code is outside of this function. So that's why in OpenMP you have this arbitrary starting point here, which is kind of an opened curly bracket without a curly bracket, the closing curly bracket, which means you can put this closing curly bracket anywhere else you want. Okay? So the opening curly bracket, if you want, is here. Target enter data, and then you map an alloc. And when you want to free it, your closing bracket, if you want, exit data, and you delete. And now you can put these two anywhere you want in your code. Yes, enter, update, 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 exit. That's how it works. Enter data. Sorry, target what, sorry? Enter data, yes. Target, enter data first. Target, update, target, update if you want to move data back and forth. And also your targets, the actual offloading. And when you're done with everything and the data no longer needs to be on the GPU, target update. Exit, thank you. Target exit. Okay, yes. A bit louder, please. A bit louder. Normally, no. Because both, effectively what the target data does is in your opening curly bracket, it does target enter data, and in your closing bracket, it does target exit data. Okay, so let's get back to the slides. I need my remote to wake up. That's good. Because something that almost seems like a troll, but remember that wonderful GPU that has 5,000 cores and everything? How many cores were you using so far? 1. So you have a massive GPU, but so far you're still using it serially. There's nothing going on, no parallelism whatsoever. So now that you know how to transfer the data, how to transfer the execution, how to save the data transfers, now we're going to re-inject all that parallelism you know about with an extra level of parallelism this time. To explain why we're going to have multiple levels of parallelism, a quick, simplified, gentle version of what a GPU architecture is like. You take your GPU, your 5,000 cores are not in a single group of 5,000 cores. You have something called streaming multiprocessors. It's like on the host. You have CPUs which have cores. And typically what we have is we have 2 CPUs, 2 multiprocessors, which have multiple cores each. It's the same on the GPU. You have many streaming multiprocessors, each of which has cores. We have multiple terminologies here. Okay? So we're going to have one level of parallelism to use the streaming multiprocessors and one level of parallelism inside each streaming multiprocessor to use all the cores. Okay? So we're going to see that teams construct. What it's going to do is it's going to create multiple teams. Okay, so far it doesn't really help much. Or is it that I see it after? No, so I'll say it now then. Every team will be running on a streaming multiprocessor. I will start to say SM from now, streaming multiprocessor, okay, not something else. So when you will have teams, you will be able now to start using multiple SMs at the same time, so you will no longer be stuck on a single one. You have a code in an associated structured block. That's a fancy way to say curly brackets. Curly brackets. And the same way that threads by default start at thread 0, the teams by default will start at team 0. We're going to have, remember, it's OpenMP for CPU, OpenMP for GPU, which means we can now start to have the same benefits and the same conventions. Do you remember in OpenMP how you get your thread ID? OMP, yes. OMP get thread num. That gives you your thread number, your thread ID. And how do we get the total number of threads? OMP get num threads, yes. It's going to be the same with teams. You want to get your team number? Okay, well, OMP get team num. You want to get the total number of teams? OMP get num teams. Period. Okay, that's where it starts to become useful also to have OpenMP for both CPU and GPU. If you want an example, this is how it works. OMP target, why? For the same reason that you don't call OMP get num threads outside of a parallel region because you just have the blue arrow, you don't have the red arrows yet. So if you want to count how many teams you have, you must be on the GPU. So, target. And then you create your teams. If you don't create your teams, you just have one. And then you can get the number of teams and your number in that team. Or is it? Okay, just the team index in this example. Okay. As often in OpenMP, to make your life easier, we can combine them into a single directive. Okay? That's a bit nicer. Now, like parallel, remember in parallel you can use num threads to control the number of threads you want to spawn in that parallel region. It's the same thing here with teams. You can be in control. You can pass the num teams. For threads it's num threads, for teams it's num teams. So far so good. Now, since I have to be absolutely precise, the number you're going to give will be the upper cap, the upper boundary of the number of teams to spawn. If you ask 30 teams, it's just a way to say that the GPU may not be able to spawn as many teams as you would like for some hardware reasons. Maybe it can spawn only as up to, let's say, 200 teams, and if you ask for 2,000, it will give you 200. And to make sure this is accepted, the standard has to be precise and say, at most, X teams. That was for the annoying bit. Anyway, you can still say num teams and pass your value, okay? And unless you ask for a very specific fancy number, normally you should be fine. However, so now you have multiple teams, congratulations, you can use multiple streaming multiprocessors. But inside each streaming multiprocessor, you still only have that blue arrow, that master thread. You don't have the other threads yet. Do you have an idea how we could spawn the other threads? How we could move from the blue arrow to the red arrows? That's where both OpenMP start to join. You just have to use your good old parallel. And from that point onward, everything you've seen yesterday, you can re-inject it here. So now that you've seen the GPU-specific bits, now that you're seeing the link between GPU and CPU, you understand now that what you've seen yesterday was not restricted to CPUs, actually. All the techniques, all the principles, or the synchronization methods you've seen yesterday, they're right here. Okay? So, yes. It comes down to the GPU architecture. In the GPU, you have 5,000 cores. I'm going to give random numbers here. I'm not sure it's the right distribution. Let's say you have 50 streaming multiprocessors, each having 100 cores. So when you create teams, you will have 50 groups of one person each. So you can have up to, well, it's like here, we have one room with 50 spaces, but we may have 2 students in it, or 1 student. So creating multiple teams means you're taking multiple rooms, which can accommodate up to 50 students in each. But if you call teams, just put 1 student in each room, which you will call the master thread. Okay? If you want to use 50 students per room, now you need parallel. And if you use both combined, you will use 50 students in each of the rooms, which is what we want to have. Loops. What does that do? So I have a big loop, and I have multiple teams. So of course, what I want to do is I want to have these teams sharing the loop iterations. What do you think is going to happen here? What, sorry? So that's a very intuitive interpretation indeed. Who thinks the teams are going to split the iterations? So like team 1 takes the first 2 iterations, team 2 takes the 2 iterations after that, and so on. Okay? Yes? That's a very sensical reaction. Sorry? No, we're just talking in terms of teams here, in terms of the groups. Okay, group A, regardless of how many people in there, will take the first 2 iterations, and group 2 or group B will take the 2 iterations after that. Okay, and the other one, who thinks that all teams will do the entire loop every time? You're absolutely right. It's exactly what happened on the CPUs. On the CPU, if you wanted to split the iterations of your for loop, you had to use parallel and for. It's exactly the same thing here. Except that, except that if you want to distribute, you just need to call the distribute clause. Is it a clause? Yeah, it's a clause. It's a clause. And that's going to split the iterations across the master thread of each team. Okay, so it's like per room, you have 1 leader, and you're going to go and see that leader, even if there are 50 people in the room, you're going to go see that leader and say, hi, your room will have these 30 iterations to do, and you go see the next leader in the next room. Okay? So this is how you can do it. Target teams, so target transfer to the GPU. Teams, I now use all my SMs, streaming multiprocessors, and I want that for loop not to be executed entirely in each team, but across the teams, so distribute. Okay, we take it step by step. We can, to save some time, combine the 2 again. Okay, so now we're slowly getting closer to what we call the holy grail in OpenMP GPUs. You'll see way at the end. Oh, okay. We have the schedule. Oh, yeah, go ahead. That's coming in a few slides. Right on time, you're right on time. The schedule, the same way you have schedule for CPUs, you have schedule for GPUs. Just a different name to make sure we don't confuse them, so you can really give the two distinctly. Dist schedule, the same way we use distribute, we have dist schedule. Simple. On the GPUs, for now, we just have the static. If you don't use explicitly the schedule, it will use whatever it can behind the scenes. You still have the chunk size. You can still use the chunk size yourself. So you can call your distribute. By default, it will use the default schedule that the GPU is aware of. Or you can ask explicitly for static and some chunk size. Make sense? Yep. Sorry? So this one relies on the default. No, the default on GPUs is what the GPU will do. They may use some fancy things that is not static. But the ones you can give explicitly yourself, it's just static for now. As the support will improve, I guess we'll see more scheduling kinds popping up. Now, nested loops. So if I do this, yes, I have the outer loop whose iterations are scattered across the different teams. So it was my example of I go to each room and I give it to the leader in the room. But the inner loop is not parallelized. Okay, I just give one big loop to every leader, but that loop is not parallelized. You could say, oh, well, then you can parallelize the inner loop. Yeah, but that's a problem now, because it means I would go see every leader for every iteration of the loop. Because now at every iteration of the first loop, I go to the GPU and I create the teams and I distribute the inner loop and I come back and I go to the next iteration and I repeat. So what we can do now is we can use the two levels of parallelism you've seen. The outer loop, I can distribute that across my streaming multiprocessors to say to the first SM, you will have this for loop, the one in the first iteration, it's this for loop. I go to the second SM and say, okay, you will have the second iteration of the big loop, so you'll have this for loop to do. And then inside each SM, when I receive the for loop, I will say, okay, so I have this for loop to do with all of you, so we're going to split the work. So we're going to do one iteration each and so on. And now that uses the parallel for that you know of, okay? So now it's multiple levels of parallelism. And remember, that's just to use one GPU. By the end of the session, you will learn how to use multiple GPUs. So you will have a level of parallelism to use every core in a given streaming multiprocessor, every streaming multiprocessor in a given GPU, every GPU in a given node, and if you go to the MPI session, every node available. Plus also all the CPUs on top of all this. And FPGAs that may be around. Now it becomes interesting. So if you have a massive, massive, massive loop, you can just combine everything at once. So that says, I'm going to do that on the GPU, target. Create my teams, so I use all the streaming multiprocessors. Split the for loop across all the SMs, across all the teams. In each team, parallel, spawn the thread, so I use all the cores. And in all these cores, split the iterations again between that. So you're going to have this two-level distribution for a single iteration set, okay? And all this in one line. You drop what? 1, 2, 3, 4, 5, 6, 7 keywords and a hashtag. So basically, if you want to look super fancy, you go to a center where they don't know OpenMP on GPUs yet. You go to their GPU code or a code that is really slow, which would benefit from GPU. You come, you drop this one line, and then you say, yeah, HPC. So well, enough of me talking, time for you to enjoy.